Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing. This is lecture number 54 and we will be extending our knowledge now to a 2-qubit system. Till now all my previous lectures, if you have noticed, were based on single qubit and its transformation. This is probably the first time when 2-qubit will be required, understanding is required. So let me give you a brief outline of the lecture. We will be looking into silicon based 2-qubit system, right. We will go through the charge stability diagram, gate sequence and control strategy, qubit control via Rabi oscillations, Bloch sphere we have already studied. So now we need to look into its rotational principle as such, then correlations and then CV characteristics of a standard qubit logic device. So as I discussed with you earlier that if you are looking at transmon, you use current pulses, and if you are working with spin qubits, you use voltage sources, right. And this is for operations on single qubit. Now if you do a readout, then it measures basically the qubit states through resonance frequency or impedance techniques, right. So the idea here is that you send a signal, the reflected signal is studied, and you can then from there understand the state of the qubit. So as I discussed to you earlier also that we use microwave resonators for transmons, and we measure the charge impedance for spin qubits. So for spin qubits we measure the impedance of the charge detector, and for transmon based qubits we use microwave resonators. Now what are the noise requirement for readout circuitry? These are standards which you need to be very careful about. Readout circuitry must have very low noise, right, must have very low noise, right? It should be very low noise, and noise level should be less than 40 picovolts per root hertz. So this is basically 40 picovolt per root hertz, right. And this is for good SNR, this is the requirement, and SNR should be greater than 0 dB, right. And this is important because these are the limits which you set. So you can understand that the noise level, the noise floor is so low, it is about 40 picovolts per root of hertz, and that it's picovolts means 10 to the power minus 12. So 40 into 10 to the power minus 12 volts. Now if your signal floor is almost the same as your noise floor, then that's the problem which you will face when you do any single qubit or even a 2-qubit operation. Your SNR should be greater than 0 dB for a reliable qubit readout. Now the diagram which is shown here, this is part A and this is B, right. Part A is basically the device structure of a 2-qubit logic device, and part B is the SEM image. So this is the SEM image, this is the SEM image, and if you see correctly, this is the logic structure, the device structure, and it is basically fabricated on an isotropically purified silicon to minimize decoherence. That is very, very important. So the process steps are also very, very stringent in case of a 2-qubit logic device, because any small changes in the lattice will result in decoherence of the qubits. Now typically if you look here, I have this controlling gate G1 and G2, and G1 controls qubit state Q1, this is cube, and this controls qubit 2, right. The spin qubit it can be and it is hosting 2 qubits Q1 and Q2, and G1 and G2 basically are defining the quantum dots here, and GC is basically defined as the confinement gate. This is the confinement gate, this is the controlling gates G1 and G2 for Q1 and Q2 respectively. Now if you look at the right hand side, this is my ESR, right, and this is my single electron transistor here, and you have these gates G1, G2, G3 and G4 here, and this GC is basically your confinement gate, and this GC runs like this, right, like this, and by giving an external pulse you will be able to control the state of the qubit, right. And therefore generally we use a single electron transistor to use for charge sensing. So what does it actually do is that you sense the charge, and you can actually sense the charge or the spin qubit for one single electron, and that's the reason it is known as an SET or a single electron transistor. You have an ESR which is electron spin resonance, and these applies on an AC current IAC, creating a magnetic field BAC for spin control, right. This is for spin control. You basically do so you see the green colored on the SCM image is basically my ESR, right, is an electron spin resonance, and this is responsible for creating a magnetic field and for proper coherence of the qubits. If you look at the charge stability diagram, and this is the y axis is basically the variation in the gate voltage, and x axis, y axis in gate 2 and x axis is on gate 1, and this shows me the charge occupancy state. N2 N1 is the charge occupancy state in gate 2 and gate 1. So when I say that when your gate voltage is around 1.4 G1 and your G2 is somewhat 3.5 volts, you see that typically the charge is 20. So 20 means the second state and the 0th states are occupied in a proper sense. As you go on decreasing the value of VG2, you see the x component actually starts to go down, and you end up having a 0 state being populated for a low value of gate voltage G2 and a low value of gate voltage G1. If as you move to the right side, which means that as your gate voltage goes on increasing, the N1 state goes on increasing. The state at which N1 becomes stable goes on increasing. Why? Because more higher and higher gate voltage means better confinement and better this thing. So you see, if you go from left to right, it is 0, 1, 2, 3. This is 0, 1, 2, 3, 4, 5, 6, 7, which means that if your block of gate voltage is from 1.4 to around 2.2, you can actually see that the control is very stable, and you can populate the occupancy states more and more for a larger gate voltage. And the SET currents, bright lines means these are the bright lines which you see. This is the red bright line and this is the blue lines which you see. The blue lines and red lines are primarily used for detecting these transitions, right. So for example, the red line shows you a transition from gate 1 to gate voltage transition, and the blue ones are basically your gate 2 transitions, right. Now if I put a microwave pulse on Q1 and Q2, then basically these are known as Rabi oscillations. Because when you put a microwave pulse, please understand these pulses are always time varying in nature, going high and going low and then again going high and low, and your spin qubit also matches with the spin of the microwave pulse, and that is the reason you see these are all sort of Q1 and Q2 are both oscillating in a manner. This is known as Rabi oscillation, right. This is known as a Rabi oscillation, and this is for both Q1 and Q2 as a function of microwave pulse time. So this is tau, right. So this is the time pulse. So as you move from left to right, you are actually increasing the pulse time and you are able to do it. The top plot is basically spin flip probability, this one, right, and this oscillates sinusoidally, which means that there are stable states where your flipping will be almost 0, and there are unstable states where the flipping will be probability will be relatively high, right. Similarly, if you look at Q1 shows similar behavior, and therefore much better control in Q1 is expected and coherent control is there, right. And then the method is known as Stark shift to use individually address each qubit via ESR. So this is the technique of qubit control. Now let us look at the gate sequence and control strategy. Now the pulse sequence for performing a readout or initialization of qubits Q1 and Q2, and I am assuming it to be single qubit as well as 2 qubit operation. Now so if you look at this is the ESR value, ESR which you are inserting, this is gate voltage 1, and I have Q1 here, Q2 here, Q2 here, right. Now you need to do and read an initialization here, and then when you initialize Q2, you are reading Q2, and when you are initializing and when you are reading Q2, you will be read Q2, you will be able to read the Q2, and initialize Q2, you will be doing initialization. This will be red one is for reading and initialization of Q1. Now this ESR lines is used to drive the qubit rotation via a microwave signal, and that is what I was talking in the previous lecture, that you send your microwave signal to these ESRs, and they tend to act on the microwave signals, and they drive the qubit rotation. So the qubit rotation will be either shifting to pi/2 to the clockwise direction or pi/2 to the anti-clockwise direction in the Bloch sphere, and you will be able to detect its value by using these concepts, right. So if you look at the voltage signal, the voltage is high here, and as the voltage goes low, you are able to read or initialize Q1, voltage goes high again here, and then you are able to read R2, and then there is a voltage here which is Vp, and from Vp you are actually trying to measure the value of the CZ value. The CZ value is the controlled Z gate, and this is implemented via using a pulse VCZ. VCZ is this pulse which you are using, and using a tau Z value here, right. and for a duration of tau z you are using this pulse, and from this you are able to read the external signal here. So you can see you can read q1 here, right, and then q2 here and q2 here, right, and this is basically a 2-qubit control. So as you can see very easily, 2-qubit control is relatively more difficult as compared to a single qubit control. Now let's look at so as I was discussing with you this concept here, this one, let me show you the charge stability diagram for occupancy. Now this one is again the charge occupancy diagram. Now the charge occupancy states are in this case 1 0 or 0 1, which means that 0th state and 1 state for n1 and n2 respectively are occupied, and this is so the charge occupancy states are shown as a function of Vg1 here and Vg2 here, right. So Vg1 Vg2 happens to be the charge function state. These are the transition places, these are the transition ones, right, the blue colored lines are the transitions ones. Now the highlighted portion, which is this and this, which is R1 R2, so you are reading an initializing gate 1, reading an initializing gate 2, and you are able to do a controlled Z gate for extracting the value of the information, right. And the single electron transistor, as you can see, is used for spin dependent charge detection. So depending upon the state of the spin, you will be able to detect the charge, the type of charge which is stored here. Now let's look at the Bloch sphere rotation and spin up fractions. Now if you look at the left hand side diagram, again it is the same thing, initialization and then applying a C0 gate. C0 gate is almost like an inverter gate. Now the upper slot, this is the upper slot and this is the lower slot which we are saying. The upper slot shows spin up fraction for both qubit after initialization and applying a C0 gate. So what I do, I initialize it, both 2 qubits, so one is up, another is down, and then I apply C0 gate, and then I apply C0 gate, and I do a so I apply a rotation by pi by 2 by using either a poly X or a poly Z gate. I also do this rotation, and then I do pi by 2 on the X axis. If you go and try to find out the spin up fraction, then since you are only, this is what I know, this is what is known as I am trying to only control the blue colored qubit, right. The red colored is still kept at spin up position, and therefore you see its fraction spin up fraction probability is very close to 0.8 or 0.9 and it remains stable if you find the value. But interestingly, this value goes up and down, you see, this value goes up and down, the blue colored goes on up and down, because the probability of spin up reduces when it is in any other state as compared to spin up. And therefore you see, if you do this one, this is minimum value which you get, right. Similarly this one also gives you a minimum value. Now if you look at the lower graph here, it's just the reverse, that you now have spin down. So the red colored curve here is actually at very low spin up fraction probability, and your spin up remains the same, it almost goes like sinusoidal signal which you see. So the Bloch sphere rotational shows the conditional dynamics of the system. So just the Bloch sphere vector which rotates up and down will showcase to me the fraction of the total time that the spin is in the up qubit state. Now 2 spin q relations, though ideally you do not want it to happen, but this happens quite a lot, that the 2 spin will actually correlate with respect to each other. Now what I am showing is basically spin probability of different 2 qubit states. This is a up state, this one is up state, let us suppose this one is up state and this is up down state, and after a C0 gate. So after a C0 gate I will get, so apply a C0 gate I will get up down. Now so there are two types of, so they are either correlated or anti-correlated. Anti-correlated spin behavior is clearly observed in this case as expected from a C0 gate. So when you apply a C0 gate functionality on a 2 qubit system, anti-correlated spin behavior is visible to you. If you look at the green inset here, this shows initialization followed by a C0 reply. The black lines are basically the model fit parameters, and the green dotted lines which you see, the green dotted lines are basically the expected ideal outcome for maximum entangled states. Now if you look at 2 spin, so this is on the x axis is 2 spin probability for all the 4 graphs. So when you initialize it and there exactly in the opposite spin, this shows with varying value of microwave pulse time tau p, this goes on varying as up and down, right. It is almost like a sinusoidal wave. However, when the same 2 qubit state is there for a fully correlated states, it is almost constant and it remains either high or low, but it remains constant because it is highly correlated with respect to each other, right. So, the correlation and non-correlation comes into picture. Let me come to the spin qubit states and explain to you what the spin qubit states. We will summarize the working flow. In this case, we will look into the array of spin qubits and working of the spin qubits, and then multiplexing DC and IO signals, and multiplexing DC and IO signal will important for understanding it. So, let us look at the spin qubit sort of a setup as such. The typical readout setup for spin qubit understanding, right. Now, the first thing is you have a voltage source here, right. You have a voltage source, a buffer, and then this, the blue colored is this one, is basically the spin qubit is located in the center of the dotted circle. So, if you look very carefully at this graph, this is I have taken a photograph of it from a reported literature, and this is basically the dotted curve which you see here. Within the dotted curve you will have the spin qubit. This is a SEM image which is being located here. The control and readout circuitry are via M, P, R, T and Q gates. The quantum point contact is shown as a part of the readout circuitry, right, and that is a part of the readout circuitry which generally is. The voltage source is implemented and you apply a ADC here, right. Digital to analog converter will be there, the quantum device, and this operates at around 20 millikelvin. This is where the whole idea of the quantum state is being superimposed by using an RC network, effective RC network. The signal path, if you look very clearly, there is a quantum resistance and there is a parasitic capacitance is associated with any. So, this is almost like a simple network theory course where any active or passive active device can be actually converted into a voltage source and some passive networks. So, the voltage source is capital V here, right, and the passive networks are the quantum resistance here RQ and the parasitic resistance CL here. So, this and this are primarily the equivalent R and equivalent C value which you see. The signal condition is done via low pass filter and ADC, right, and this is your band gap reference current or voltage source, and you do an ADC here. These are all sitting at 300 Kelvin, your qubits are at 20 Kelvin. Now, the inset actually shows the source drain current path, right, and so the source drain current path is basically this one here. So, I have a source at this end, I have a drain at this end, and the current flows from source to drain between the reservoir through the dot. So, what we do, we initialize the spin qubit, and we have already seen that we initialize the spin qubit by using a gate controlled state. Then we manipulate the spin state using microwave pulses. Again, as I told you, the frequency of the pulse and the pulse width will determine how do you manipulate the spin qubit state. Type of gate which you use will also manipulate whether you are doing pi by 2 phase shift or pi phase shift in the Bloch sphere case. Then we look into the readout for the spin state using quantum point contact, right, and then we amplify or filter the digitize the current analysis for analysis purposes. Now, let us look at the working principle. Obviously, the continuation of that, the single electron spin is confined in the quantum dot, right, indicated by the dotted circle here. As I discussed with you earlier also, the spin qubit is defined by M, P, Q, R, T, which shapes the quantum dot potential, controls the tunneling coupling between the dot and the reservoir, and it enables initialization, manipulation and readout. So, basically these gate, so if your coupling is not strong between the dot and the reservoir, quantum dot and the reservoir, the change of state will not happen very frequently, right, and therefore, you need to have a much control and much higher tunneling coupling between the dot and the reservoir. And then you need to therefore enable your initialization process, manipulation process and the readout process. Let's go one by one and see how you do a spin initialization. Now, obviously the electron will be loaded into the quantum dot from the reservoir and you will do a very controlled quantum tunneling here, right, and this tunneling will help. So, this is the reservoir which is here, this is the reservoir, right, and this what you see here, the double sided 2 arrows are primarily responsible for the tunneling from the reservoir and putting it in the quantum dot state. Now, if you apply specific voltages, gate voltages, the qubit will be initialized into a known state. So, the very fact that when you do an initialization, you should be very clear about the state of the spin or spin up or spin down state. If you are using a spin qubit, its state should be known a priori in a much better manner. Then what do? You do spin manipulation. How do you do it? As I discussed with you, send a microwave RF pulse and you perform RF spin rotations, right, and these pulses will flip the state from maybe bottom spin to top spin, and depending upon the pulse duration and frequency, which we have already seen in our previous cases. Now let's look at the readout mechanism. This is so what we do is we try to correlate the spin of the electron to the charge of the electron, right. So the spin state, as I discussed with you, is mapped to the charge state, right, such that you by what, by tuning the gate voltage. So what you can see is that maybe one spin state, say top spin state, tunnels out of the dot, and the other spin state remains within the quantum dot area. Now the idea here is basically, so therefore there is a selective sort of filtering which happens here, and you only filter out all top spin through tunneling mechanism, and you put it under into the quantum dot states, and you remain all the low down spins or top down spins bottom in the confined to the reservoir. So the probability of finding bottom spin will be much higher inside the quantum dot, and a higher spin up will be more probability will be found outside the quantum dot. Now the QPC actually senses whether the electron remains in the dot or has tunneled out, right. So if you know that electron has tunneled out, it will spin up, it is remaining inside, will spin be down, and this therefore indirectly tells me the state of the spin, right, and that gives you a very good idea about it. Now if you look at the cryogenic operation zone, and this is at 20 millikelvin we are referring to, this blue colored rectangle, the blue colored rectangle which is kept here where you have RQ and CL, this is basically your quantum state where it is stored, and they are operating obviously at very low temperature using a dilution refrigerator. The QPC current through the quantum resistance couples with the parasitic resistance. So therefore there is a RC network which happens here, and the quantum current which is flowing here passes through the quantum resistance and then couples with the parasitic cap. The parasitic cap therefore charges to a high value depending upon the current which is flowing through the RQ value. Now you need to do a signal conversion and processing. Now current will basically flow from QPC, is converted through an IV converter, right. So if you are measuring the voltages, you need to do an IV converter, and this is basically what you do, and pass it through a low pass filter to remove the noise, right. So low pass filter means all low frequency noise will be removed, will be allowed to move forward, and all high frequency noise will be stopped in this case. And the analog signal is digitized using a ADC which is kept here, right, and this is at room temperature, and then obviously this ADC will be attached somewhere to a DAC in order to ensure a proper voltage across the circuitry. Now let's look at the 1D error of spin qubit. So this is how you actually do it. Now you can see, as I was discussing very early in our discussion, that there is a mux and demux required, and that is what you see here. You see you have a demultiplexer here and you have a mux or a demux kept here. Now these pink circles are basically your quantum dots. These are QDs having a spin up or spin down states, right. These are QDs which is visible here, and therefore see these quantum dots are basically quantum wells. Since quantum wells will have very restricted and well defined energy states, very discrete and well defined energy states, I can a priori predict the value of the energy levels if I know what is the dimension of my quantum dot. The spin of the electron in this case happens to serve as the qubit. Now this QD, or the between the two quantum dots we insert quantum barriers, right, tunneling barriers, and the thin vertical gates between quantum dots are primarily used to control the tunneling current. So there will be a tunneling current between the quantum dot and the reservoir, and by using these thin vertical gates we will be able to control the tunneling coupling. Now if you look very carefully here, I have a mux or a demux here. If I have an external signal which is coming here from the DAC, and these are kept at higher temperature, you see these all are kept at higher temperature, right, these are all kept at higher temperature, these are all kept at lower temperature. So there is a differential gradient which is happening inside this quantum dot. Now this mux will choose which of the vertical thin gates you are applying potential to work as a tunnel barrier, right, or tunnel coupling barrier, and therefore it is important to have a mux at this particular point. And that is the reason you have a mux and demux, that you can, using mux and demux, you can control which of the qubits you want the tunneling to happen and which of the qubits you do not want the tunneling to happen, and that is the reason you can do it by an external potential which is coming from the DAC. Now these are also the things, there are thin vertical gates and there are thick vertical gates. The thick vertical gates are referred to as plunger gates, and they control the electron occupancy in each dot. So electron occupancy primarily means the state You remember when we were discussing just now the availability of state 1 and 0, these plunger gates control the electron occupancy, and they are primarily used for qubit initialization and state stability, which means that how do you initialize your qubit, and you need to maintain the stability. So, when you want to maintain the stability, you do not want the tunneling to happen, you raise the potential of the plunger gates and they will have a larger tunneling barrier, and that will ensure less amount of probability of tunneling across the network. Okay. These yellow crossed wires, which is this one, you can see on the right hand side, these yellow crossed wires, right, cross squares, are known as charge reservoirs. This is where, and these are located at the edge of the array, and they are primarily used for loading and unloading of electrons holes from the quantum dots, and they are again with plunger gates are responsible for initializing or resetting of qubit pulse gate. Okay. Now we come to the charge sensor dot. The charge sensor dot is the top QD which is connected. So, this is my decoupling rate, and this is the charge. So, the top quantum gate, this is the top quantum dot which is connected to DMUX, right. This blue colored sort of gate here is basically known as charge sensor dot, and it capacitively couples to the qubit, and therefore it detects how much amount of charge movement is being available to you without disturbing the qubit spin state. So, therefore, this is almost like a non-destructive readout circuitry, and this is quite critical for understanding one array of spin gate qubit, that you do not want that the state should be destructive. So, the state, you should read the state without destroying the state. Let us look at finally at the mux and demux here, and they will obviously be used to reduce the wiring. You do not want the wire to actually clog your quantum dots, which anyway are kept at millikelvin, right. So, use multiplexers and deep multiplexers to reduce the number of connecting wires, right, and you already know it from basic electronics how it works. And they help route the multiple signals across a fewer interconnects, which means that if you have a lesser number of interconnects, you will have lesser EMI and electromagnetic interference will be bare minimum, and whenever you have scalability of qubits, you will automatically have a much larger number of interconnects requirement, where the requirement of mux and demux becomes essentially very large. Okay. So, the idea is that we have already discussed the initialization. So, electrons are loaded on the quantum dots, that is the first thing which you do. Then you control the gate voltage for the loading process. Then the thick gates are responsible for holding single electron in those quantum dots. How do you manipulate the qubit? We have just now seen that tunneling barriers can be used, and I should ensure that the control qubit interact and stay isolated is done by this thing. And finally, the ESR pulses are routed across the network by an external microwave ESR, a microwave or a ESR pulse, right, you can do that. How about readout? The spin state is changed to charge state. We have seen this point just now. There was an IV source meter also, and so if there is a charge sensor, it detects the charge, and then the sensor reads out using a shared mux or a demux line. So, I have a shared mux line available to me, the state of the charge is available through the muxing of the line, and from there I can extract the value of the output voltage. Now, this is again very simple and straightforward, but you need to know why is it like this, that if I take let us take a 4 qubit example, which means there are 4 spin qubits available to me. So, typically for each qubit we require 2 to 4 DC gate lines, 1 to 2 AC microwave IO lines, and 1 readout line, right. Now, this is just for 4, right. Now, which means that there are 10 to 20 physical lines for just 4 qubits. If you increase it to 25 or 30 qubits, there is an exponential increase in the number of physical wires which is being routed through the system. This will add to the thermal load in a millikelvin range. So, understand your range is at somewhere around millikelvin, right. These excess wires will actually add to the thermal load, right, and therefore, it is impractical to use it beyond a particular point, and that is the reason you require a multiplexing of DC and IO signals. Moreover, it occupies a large space. Please understand that the area where you are maintaining this 20 millikelvin is primarily cryostat. That area is that volume is very small. So, I need to reduce the number of physical wires as much as possible, and that is where multiplexing helps to solve this problem statement. As I discussed with you, they help you to share the readout and control resources, reduction in wire count, obviously integration with cryogenic electronics is much better because of less thermal load, and you have a flexible configuration. Flexible configuration primarily meaning that by using the same set of 4 wires, I can route bias signals as well as signal for the manipulating the qubit. And therefore, basically multiplexing is one of the most important part which a designer needs to know when basically scaling up of quantum processor is required, right. Okay, as I discussed with you, you can see how, so you need, this is all repetition of what we have said earlier, but if you see, this is what I am giving. I use an S in and S out signal, and this is getting multiplexed to S1, S2, S2 and S3. So by giving a control signal at this particular point, I can actually control these 4 qubits individually, right. If the multiplexing wouldn't have been there, I would have actually used 4 external signals to work ahead with. That gives you a much larger line, and this is how it is done. You use a thermometer encoder, and depending upon the value of the thermometric encoder, you can actually do a multiplexing. So let us suppose this one is high and these all are low, then M1 to M4, M3 is switched off, M0 is switched on, and S0 transfers to S in and S out, right. Similarly, if M0 is switched off and M1 is switched on, and M2 and M3 are switched off, then S1 goes to S in and S out. So this way we control the IO signals in a manner. So with this idea, let me recapitulate what we did till today. I gave you a basic architecture of a 2-qubit system, basic architecture. We looked at mux and demux, in this case at cryo, and we saw how is it responsible for reducing the thermal load and the interconnect load. We also saw various mechanisms of quantum dots and how I am able to convert a spin to a charge for extraction, and I should have an IV current to voltage, which goes to a LPF for removing the noise, goes to an ADC for converting the input voltage to a particular value. And then we saw the fidelity gets improved if you have much better control over the 2-qubit system. So scalability, so this lecture was primarily understanding of the scalability of a quantum dot or a quantum system. Higher qubit systems scalability can be understood here. So with this, we come to the end of this lecture. Thank you for your patient hearing. Till we meet next time, goodbye.